Okay, thank you. Thank you for coming back. So we have been, just to summarize a little bit, we saw some definitions of earthquakes and how earthquake occurs, and some faults, focus or hypocenter, and what epicenter mean. And we saw more terminologies on seismograph, seismogram, what a main shock is, and what a foreshock is, which precedes the main shock, and also the aftershock, which are usually less magnitude earthquake compared to the main shock. We have seen seismic waves and seismology. Seismology is a scientific study of earthquakes and the propagation of elastic wave through the earth. If you can mute your mic, I appreciate that. So seismologists are usually, in this course, you'll see an overlap between seismology and geotechnical engineering and structural engineering. Normally, all those fields, they go together. The seismologist is the one which go much deeper into the interior of the earth and studies the content of the earth like a geology, but related to seismic activities. So they study the study of the a scientific study of earthquake and its propagation through the elastic media of the earth. So from the source to the surface, it's usually seismology. Geotechnical engineering is around the surface where buildings are sitting, the top, the few hundred meters on the earth. So we receive the input from a seismology study and we convert it to a usable for engineering application. And as a geotechnical engineering, we're supposed to understand the soil, the nearby soil around the structures. Then structural engineering is also based on the input from the geotechnical engineering. So you will see interaction between these three fields: seismologist, geotechnical engineering, and structural engineering. Because when the earthquake comes, it comes like in a wave, just in one shot. So even if we divide it into three, they are interrelated. So earthquake causes, theories, and world high seismic areas. For cause of earthquake, we know that it happened at a fault, but you can have a natural cause like a tectonic activity. Tectonic activity is the top, the crust plate is moving around. You can have a tectonic activity causing earthquake naturally, or a volcanic activity. Those plates on the top of the earth, they move because of that hot molten volcanic activity under them. So when a volcano erupts, it can also cause earthquakes. Or you can have also man-made or artificial earthquakes, which are a controlled explosion. Sometimes when they do these nuclear tests, nuclear missile tests underground, that can cause waves to propagate similar to a seismic wave. Or a mining activity. When they are drilling for a mining activity, they can run into a fault and break rocks and causing some earthquakes. But these man-made earthquakes are usually minor. And probably you have heard, North Korea usually tests nuclear missiles underground. Those, I think the last one, it was recorded around 5 on the Richter scale. It was tested in North Korea, but it was recorded in even North America. So it can get higher. But mining activities or hydraulic fracturing for a gas and oil drilling. They drill, put water with pressure, which is they call hydraulic fracturing, and that can cause some faults to move further and cause some minor earthquakes. Or construction of dams and reservoirs. Heavy dams on the surface, that especially if there is a fault underneath, that can cause also some minor earthquakes. So anything which causes some strain and movement along existing fault or breaking of existing rocks, it can cause earthquakes. So you can have a natural cause or you can have man-made cause. But the man-mades are usually less. especially those mining activity or hydraulic fracturing in US, especially the South, the Texas area, Oklahoma area. There is a lot of drilling going on for a gas and oil drilling. And there are a lot of minor earthquakes reported, the magnitude of 3, 3.5, 2.5. And it's very common. And those earthquakes, you can see this data, magnitudes 2.5 and less. It looks, earthquake doesn't occur more often, but you'll be surprised. Most of them, they are not noticeable, but you can have millions of earthquakes, especially 2.5 and less. We don't usually feel it, but millions of them happen because the interior of the earth, everything is in motion. The top plates are in motion. And magnitudes from 2.5 to 5.4, they are often felt, but only cause minor damages. You can have 500,000 per year. And magnitudes from 5.5 to 6 on the Richter scale, they cause slight damage to buildings and other structures. You can have average of 350 per year. And earthquake magnitude of 6.5 to 6.9 may cause a lot of damage in very populated areas. You can 100 of them. And 7 and 7.9, major earthquake, that's what we call them. Serious damages, you can have 10 to 15. And above 8, it's rare. Even 7, this seems larger recently. But you can have them at least once every year or two. So there are so much going on under the earth, and you have a lot of minor earthquakes, even if we don't feel them, especially in the Rift Valley, Ethiopia. That's a diverging plate. You have, especially Arba Minch area, you can feel these minor earthquakes. So epicenter of 30,000 earthquake recorded during 1961 to 1967. So this is what researchers observed. They recorded earthquake from the 1961 to 1967. That's about 6 years of duration. Then when they locate the areas when they are happening, this is what they observe. All these red and dark dots, that's where they observe them. So you see it on the western part of US, western part of South America. Not much in Africa, but you see it in Atlantic Ocean. So all these lines. And more you see it in the Asian, eastern part of the Asian country, all this. So this is how they identified, okay, what's going on? This is where the faults are happening, the earthquakes are happening. So this gave an indication that there must be faults around this area where the earthquakes are occurring. So those are just recorded histories, data. So faults are fractures inside Earth where movement occurs, where earthquake occur. You can have the depths and lengths of faults vary greatly from few meters to several kilometers. This is one indication of a fault line on the ground surface. You can see it from a plane, aerial view. You may not notice it on the ground, but this is what it looks like. If you see mountains forming like this, that's clear indication of fault line underneath. Earthquakes are caused by active faults. You can have active faults or passive faults. Passive ones don't move, so they don't usually cause earthquake. But the active faults, they are constantly in motion. And when that accumulating strain energy exceeds the strength of the rock, then it breaks. That's what you get, earthquakes. And type of faults, if you assume this layer of mass of soil, the body of the earth, if you assume some crack, you can have a normal fault where the two blocks are going away from each other. So these arrows are showing you when they are going away from each other. We call it also diverging fault or normal fault. When the two faults are converging to each other, that's when, friction happens. We call it reverse fault or converging fault. Or they can just slide one another. Strike and slip fault. So these two are the major cause of major earthquakes. In the case of normal fault or a diverging fault, they are going away from each other. course, when they break, there will be some earthquake, but usually it causes minor earthquakes. But the major ones come from a reverse fault and strike slip fault. So common fault movement at a plate boundary. If you see a section of the interior of the Earth, let's say this is the crust and the top portion of the mantle, where it is a solid rock, but underneath it's more hot and more flexible. So the top portion, it can move away from each other. That's what we call a divergent plate boundary. Or it can be like a convergent plate boundary. They are going to each other. Or you can have it like a strike slip transform plate boundary. So this is, let's say, this is, you have ocean, right under the ocean, you have the crust part. It's like subducting under another crust. This is where most of the oceanic trench or the earthquake occur. Or you, because of this bending, if you see this crust, you can have a molten magma coming out. We call it volcano. This is just to show you in a view. And if you see the interior of the Earth, if you open it up and see it, of course, nobody went inside. These are models. So the Earth has four major layers. You have the crust, the mantle, the outer core, which is liquid, and the inner core, which is solid. You know, when I was in elementary school and high school, I was educated that the core is liquid, but it's not. The inner core is solid. We will see how they observe it. Maybe you have a better classes and you probably know about it, but in my time, we were educated the interior of the Earth, which is the core, is all liquid. But it's not the case. The most interior, it's solid. So you have the rock, the crust area, and you have the mantle, upper mantle and lower mantle. Usually upper mantle is like a crust, it's a rock, solid rock. But the lower mantle, because it's close to the outer core, the outer core is liquid rock, or semi-liquid. This rock, the lower mantle, is also semi-solid. It's like a hot metal. So if it's more flexible. So if it's flexible, it doesn't break that much. So most of the earthquake happen in the upper mantle and in the crust area. That's where it's solid and it breaks. So especially in the top 70 kilometers where earthquakes are occurring. Deep inside, they don't occur that often. So you can see it. You have oceanic crust. Crust is crust, but if it's a continent, then we call it continental crust, something like this. If it's under the ocean, we call it oceanic crust. Both are crusts. Of course, under the ocean, it's thinner. And we have that asthenosphere is the upper mantle. This upper mantle and continental crust together, I think, it's the crust, continental crust and the upper mantle, we call them lithosphere. And depth-wise, you can have this. This is up to, I think, the first 70 kilometers. And below that, we have asthenosphere starting. So crust is made of rocks. It's granite or basalt. And mantle is mostly solid hot rocks, granite and basalt that can flow like liquid. Core is mostly iron and creates Earth's magnetic field. So the core is the one where it's responsible for the Earth's magnetic field. So most earthquakes occur within a few tens of kilometers of the surface crust and upper mantle. Shallow focal earthquake, usually 70 kilometers, 75% of the earthquakes. Intermediate focal earthquakes from 70 to 300 kilometer depths. And deep focus, more than 300 kilometers. It's very rare. So now, no earthquakes are known to have occurred below about 700 kilometers. At greater depths, like I said, the rocks are very hot and under high pressure, so they deform by flowing rather than breaking and faulting. So the shallow earthquakes are the more damaging ones. When you have a deep earthquake, usually they don't cause that much surface motions, so they are not that much damaging, or they are rarely destructive. So let's see some theories how previous scientists came up with the explanation of why earthquakes occur. So one of the theory, it's called continental drift theory. So what it says is, if you look at a map of Earth's surface, you will notice that the edges of some of the continents seem to fit together like a puzzle piece. So this is what it's talking about. If you bring all the continents together, they fit actually. This is an observation from a previous scientist, especially a German meteorologist, Alfred Wagner, proposed that the continents were once joined together and have since drifted apart. His idea was called the continental drift theory. How did he come up with that? Because he observed, shape matching. He was able to fit some geometries and also similar fossils at different parts of the world where those shapes meet, and also similar climate and similar rock discoveries at different continents. So what he said is, in his theory, the world used to be together like this, but through time, something must be causing them to go apart. So what he says is, in Permian time, 250 million years ago, it used to be like this, based on this continental drift theory. 200 million years ago, some separation, you see it. 145 million years ago, more separation. They are moving somehow. 65 million years ago, more separation, until the present day, which is what we know right now. So why these continents are moving away from each other? Well, so the continental drift theory, the theory is based on the convection current. So what it says is, this theory requires a source that can generate tremendous force acting on the plates. So we know that there are top plates, the crust and the top portion of the mantle. So there must be something causing them to move. What is causing them? What it's saying is, there is this molten magma, the outer core area. There are convection currents moving around in the interior of the Earth. So the widely accepted explanation is based on the force offered by convection currents created by thermomechanical behavior of the Earth's surface. The variation of mantle density with temperature produces an unstable equilibrium. The colder and denser upper layer sinks under the action of gravity towards the warmer bottom layer, which is less dense. The lesser dense material rises upward, and the colder material, as it sinks, gets heated up and becomes less dense. These convection currents create shear stress at the bottom of plates, which drags them along the surface of the Earth. So it's that molten rock convection movement which is causing them. Just to see that visually, let's see, there was a picture. Yeah, let's see this one first. What it says is, you have these convective currents. So you have plates on the surface of the Earth. You can assume these yellow shaded plates. So these convective currents, one must be counterclockwise. Let's say the other one is clockwise, causing a diverging plane. So this crust under this convection current is being pushed to the right, this one being pushed to the left. So we are having a diverging plate situation here. Or it can be the other way. They are pushing each other depending on how the convective currents are moving. So plate tectonic theory embraces continental drift. These theories, continental drift and plate tectonic theory, they are not different theories. They support each other. They complement each other. So all they are talking is, okay, continental drift say, oh, they are moving somehow. Why they are moving? Then they came up with this convection current theory. Then the plate tectonic theory comes. Plate tectonic theory says, plate tectonic theory embraces continental drift theory and considers the crust and the top of the mantle, the lithosphere, is made up of several tectonic plates that move relative to each other over a semi-plastic layer, asthenosphere. This is the lower mantle layer, beneath Earth's crust, causing earthquake at a plate boundary. So the plates have somehow moving because of the convective current. Some plates, you can see these red arrows. They are moving towards each other. We call it converging. Some plates, they are moving away from each other. We call it diverging. Some plates, they are moving next to each other, like a strike slip. So we know that from our fault examples, fault type examples, the strike slip and the converging plates or faults, they are the main source of major earthquakes. So you can see all the continents. We have 7 large plates. Now, if you consider this is a Pacific plate. And you can see, for example, Africa right here. This is the African plate. The entire Africa is in one major piece of plate, but there are also intermediate faults. We will talk about those. So if you see Africa, in the northeast around the Red Sea, right? I think right about the Red Sea, there is this diverging plate. And also in the Atlantic Ocean, it's a diverging plate. Also from the Australian plate, the African plate, it's diverging, which means the Australian plate is going away downward, the African plate is moving upward or upward, in the northeast direction. And the Eurasian plate, the one which is Europe and Russia, that one is also going, it depends. That one is going to the east and south a little bit. You can see it. The Indian plate is right here. You see there is the Indian plate and the Eurasian plate, a converging boundary right here. And the North American plate, this one, the North American plate is diverging from the Eurasian plate. So these 7 major plates, they are moving in this pattern, either diverge, converge, or strike slip. So this will give you a background why we are having, large earthquake only in specific areas of the world. So plate tectonic theory, the convective currents, we already talked about this. The last theory, which is still, it's a complement to the previous 2 theories, is the elastic rebound theory. What it says is it goes more deep inside how the rocks break. What it says is due to plate movements at faults, rocks deform and accumulate energy over a long period of time. When the stress exceeds the strength of the rock, it breaks or snaps back, releasing the stored energy in the form of earthquake by vibrating back and forth. You can see an example here, solid model, or you can consider a bar. If you just hold it with no strain, it's straight. Then if you bend it, now you are accumulating some energy. A bending energy, you can call it, or a strain energy. That means in the solid mass, you can have this crust deformed, strain accumulators. So this part of the crust is moving to the right, the lower portion moving to the left. So some kind of strain is happening, which is similar to the bar model. Now, when that movement exceeds the strain energy, then it breaks. When it breaks, see it in the bar example. It breaks and snaps back. You'll have some vibration. That bar moves up and down. Finally, it stops. The same thing is happening deep inside the earth with the rock. It breaks, it creates a huge energy. There would be sound, there would be heat, and there would be elastic waves traveling because it's snapping and hitting the top portion of the earth. Then we feel it as, and we call it earthquake. That's what earthquakes are. Okay, this is just a model. And then finally, once it breaks, it releases the energy. And before it breaks, this is the main shock. There can be foreshock and aftershock. Depending on the movement, you can have minor earthquake before the main shock or after the main shock. Fracture crust fault zone. So you have faults forming or enlarging, and you have a strain released in your bar example. So that's what the elastic rebound theory is. So all these theories, continental crust, plate tectonic, and elastic rebound theory, they complement each other. And they are trying to explain the phenomena of earthquake deep inside the earth. So let's see a little more detail on the plate movement. Convergent plate movements around tectonic plate boundaries when plates are moving towards each other. That's the one we said in this case. These arrows, when they are moving towards each other, Let me give you an example. For example, right here, the Pacific plate, the Eurasian plate. So when that happens, it can be, one going under the other one. We call it like a subduction zone. So this can all happen deep inside the, oceans. So we have oceanic crust. We don't see it. So that's why some earthquakes occur under sea. So you have the converging plate, one going to down, and the strain accumulates. At some point, it breaks. Every some years you'll have major earthquake, but because the energy accumulates over a long period of time, and you have earthquakes generated. So in this case, if both plates moving towards each other, if they are under the ocean, we call it ocean-ocean convergence. These boundaries are created when an oceanic lithosphere subducts beneath another oceanic lithosphere. Or you can have oceanic continental convergence. You can have a continent and you can have an ocean. Under the ocean, there is this crust. It's going under the continental crust. In that case, we call it oceanic continental convergence. Or you can have continental convergence. It just sometimes you see like a Himalayan mountain is a perfect example. So the Himalayan mountain, it's caused by the Eurasian plate, you see it here. And the Indian plate, they are converging to each other. When they converge to each other, that's when happen. You have mountains forming. And the one subducting underneath sometimes, it breaks because it reaches that strain energy level. So you have earthquakes occurring and a mountain forming. And the Himalayan mountain, there is a study which shows the Indian plate, it moves around 9 centimeters per year by itself. But the Eurasian plate is resisting its motion. So what happens is actually the Himalayan mountain, because of that convergence, it's growing. And some portion of it going under, some portion of growing. So the Himalayan mountain is growing at 3 to 6 centimeters a year, every year, because of this plate movement. Let's see some high seismic areas in the world. So based on those plate boundaries we saw, whether strike slip and converging plates, those are the major source of earthquakes. So if you see the Eurasian plate, that's where the European and the Russian plate is, and the North American plate, this is the other side of the world, the Pacific, and this is the Pacific plate. All around the continents, on the edge, this is like oceanic continental convergence. You have either converging, these dots are showing you convergence, converging plate boundaries. And these are showing you just spreading or diverging boundaries. And for the strike slip, there should be some lines. I don't see them here. So what happens is whenever you have those strike slip and converging, that's where you have the major earthquake observed in the past. And this area is what we call ring of fire. The major earthquake, especially the west side of South America, western part of North America, the eastern part of Asia, maybe where Alex is currently is, that's a very high seismic area. The Philippines area, the northern part of Australia. So that is a high seismic area. And normally it is called ring of fire. And you can also see the ring of fire is not the only place. You can see more places here. High seismic areas in the world with color contours. You can see high seismic areas, even if they are most of it is, you see the western part of US, western part of South America, and the Asian is still inside the Himalayan mountain region. See, this is India. That is a converging plate. You have seismic activities. You don't see much in African plate because the African plate I showed you earlier, most of it is diverging plate. So Africa is one of the luckiest continent when it comes to earthquake. No major earthquake recorded. We have minor earthquake in the Rift Valley, You see it in the contour here, but nothing really major. The major ones happen either in the Ring of Fire area or in the Middle East, in the Himalayan mountains area. So this is more just showing you high seismic area in the world with intraplate faults. This shows, still the arrows show you whether it is diverging. You see the African plate is diverging plate all around it. And we have also intraplates such as the Rift Valley area. We have it here. But in the Rift Valley area, it's going away from each other. It's divergent. So it's not expected to cause large earthquakes. But if you see it in the East Asia, east of China, Japan area, those areas, they are convergent. In the US, I think there are strike slip faults in the western part of US. Great African Rift Valley fault activity. So even though the major earthquakes are on the Ring of Fire, in the Middle East, in the Himalayan mountain area, all these triangles you see, still African plate has intraplates. Even if the major plate is of Africa is this one you see, surrounding all Africa, but there is also a fault in the Rift Valley, the Great African Rift Valley. African plate is diverging plate, which is it's going away from each other. So no major earthquake is expected. However, Great African Rift Valley is a concern for separating the eastern part of Africa. So even if there is no major earthquake, there is divergence going on there. So which means we have the African plate, main one going away, and they call this one the Somalia or African plate going away. They are separating. So it also touches, Djibouti, I believe, Eritrea a little bit, Ethiopia, Kenya, and more countries. So something is forming. So the Great Rift Valley, Ethiopia, you can see it opening up here. This is a national beauty, but something is going on. And what's happening underneath? Of course, some convective currents are happening. And we usually see volcanic activity underneath. So that volcanic activity is causing it and diverging. So there are surface cracks, surface formations observed. There are some researchers currently working on it. This is one example. A giant crack is slowly creating new ocean in Africa right now. So you can find this article with this link. And there's some cracks in the Rift Valley already forming, major cracks recently, actually. This is, some of it is in Ethiopia, some of it in Kenya and the southern areas. And finally, this is what is expected. These are models. Finally, what is expected is the main part of Africa and that eastern, the Somalian place separating and creating like ocean. The Red Sea, going through it. But that's like in geological time. It's not, we're not expecting this the next 10 years or 100 years. This will take millions of years. We're talking in geological time. So this is what is expected. This is another model showing. Is Africa gradually splitting into two sections? These are Google pictures, online pictures, just to help us visualize what's going to happen in the long term. There is another research work also which says Ethiopian Rift Valley may be flooded sooner than Somalian place separation. Even before it is separated, what it claims is, I think this is, let me see, I found this from seismologists from the University of Bristol and members of research teams in Afar are claiming that the only thing separating the Afar depression from the ocean is a 20-meter block of land in Eritrea. So based on the elevations, what they claim is this Red Sea actually can flow even before the Somalian plate, this major plate separate, and so there is only a block of rock which is holding it. So we may be able to see the Red Sea flowing and creating this lake or whatever, even before we see the diverging plates finally happen. So that's a research work, that's a claim. I didn't put the link, but you should be able to find it online. Example of past earthquake damages on civil structures. This is a list of, most earthquakes. We'll see some of them and their damages. For example, the 19.9.5 earthquake, the 1960 Chile earthquake, or the 9.2 1964 Great Alaskan earthquake, or the 2004 Indonesia Sumatra earthquake, and the 2011 Japan earthquake. We'll see. 2004 Indonesia earthquake, when this happened, I was in India. And the 2011 the Japan earthquake, it did a lot of damages. It changes so many things in the entire world, especially in the nuclear industry. We'll see it. I work for the nuclear industry right now at BiT Energy. So we are impacted by this earthquake. We'll see how it affected. These are the dates when it occurred and the locations, the latitude and longitude. So the 2004 Indonesian Sumatra earthquake, it occurred on the western side of Sumatra under the lake. So this is oceanic to oceanic convergence. It caused a 9.5 magnitude at the coast of the Indonesian island of Sumatra. Tsunami arrived after 7 hours and devastating coastal areas in Indonesia, Sri Lanka, India, Maldives, and Thailand, sustaining massive damages with estimated killing at least 300,000 people. So it's not the earthquake usually which causes the major damage. It's the consequence, the events of. In this case, it's tsunami. It's the entire portion of the edge of Sumatra. It's flooded by tsunami, a high wave of water. We'll see it in detail in a few minutes. Tsunamic impact reached India and as far as East Africa. It reached as far as East Africa. Some locations reported that the waves had reached at a height of 30 feet, 9 meters or more when they hit the shoreline. So just to explain you what happened here, so it occurred under the water. It's far away from the city, so the seismic vibration was not that bad. I think some buildings actually they were designed for. But what happened is it's the water. So the earthquake occurred and it caused the water to move up and down. So you have a mass of water moving up and down. And a tiny movement of the water at deep depths. Now when it travels and reaches the surface, that's what it causes huge waves of tsunami. So there are two events, I thought, 2004 and again in 2005. So tsunami can be triggered by an earthquake if there is sufficient fault movement at seafloor. Tsunami can also occur when the vibration of a quake sets an underwater landslide into motion. Tsunami is a Japanese word for seismic sea wave. So see how it happened. There is a fault movement happening right here. It's far away from where buildings or people are. But this fault movement, this vibration, it was enough to move the water a little bit up. Let's say it maybe, 1 feet or maybe 1/3 of meter movement of water around here. And that water started moving. Now, a huge amount of water moving at a height of, let's say, 1/3 of a meter. Now, when you go to the land area, continental area, the depth of that water is getting shallow, but the energy is about the same. A large mass of water, a small depth of that wave, but when it approaches, it's a small amount of water with the same energy. You need to have a larger height of tsunami. That height was the one which is causing. That's how tsunami occurs. The depth of the wave is really shallow when it originates, but when it approaches the ground surface at the shoreline, it gets too high. I heard of it sometimes like 3 stories. It can reach to 3 stories. So the entire shoreline would be flooded. Recently, tsunami warning systems are implemented in some high-risk areas around the world. Although tsunamis travel quickly, there is sufficient time to evacuate all but the area close to the epicenter. So tsunamis, they don't come immediately. The earthquake arrives within few minutes, few seconds. But the tsunami, it takes time. It gives you like 7 hours, 10 hours, or 12 hours. So once we know the earthquake occurred and when it occurred, we can actually have a tsunami warning system for the shoreline. So we give a warning to people to stay away from the shorelines. If you have 3 hours, 7 hours, that's good. You can escape at least, the tsunami impacts. So at the origin, you can see it. This wave occurred, then tsunami generated. Tsunami speed was 835 kilometers per hour. Water depth of this much. Tsunami speed 50 kilometers per hour. But now it's getting much taller. Water depth is 20 meters. The height is just increasing dramatically. So these are a few examples. Tsunami caused the most damage during the 2004 Indonesia earthquake. As the entire water mass came and flooded. You can see some areas completely wiped out. Just, it created like some small ponds where cars are swallowed. This is in the middle of the city. This is the other shoreline. You see some leftover buildings, but most of it is wiped out. Just another image, same phenomena impact, same tsunami impact. Just another view. You can go through those pictures. They give you more understanding of what can happen during tsunami. And let's see another example on the 2011 Japan earthquake. Resulted in tsunami and nuclear disaster. So the Japan earthquake, this is the Japan. It occurred on the eastern part of Japan, earthquake on March 11. The magnitude was 9 magnitude. And where it occurred, it's a subducting, the Pacific plate going under your Eurasian and North American plate. So you have a lot of seismic activity going on. And this is Japan. This is just if you take a section, a model. And what happened there is still similar to the Indonesia earthquake in 2004, 2005. The Japan earthquake caused tsunami. The vibration wasn't that much. Japan, most of the Japan buildings, even the nuclear power plants, they are well designed for the vibration. The seismic, inertial forces, they can resist it. But they were not properly designed for the tsunami. They were not expecting so high water coming from the tsunami. So this is an image, tsunami damage following the 2011 Japan earthquake. This is a live picture. Just see the street is how it's getting flooded. This is probably a picture taken from the air. So I found this picture from Google. You can find a lot more. Then this is where the 2011 Japan earthquake and tsunami forces are estimated to move Japan by 8 feet. So you can have even islands and continents even moving because of a tsunami force. So this is another estimation, what researchers found. Quake moved Japan by 8 feet. This is the United States Geological Society. The tsunami force is so high, it's able to move even islands. In 2004, when the Indonesian earthquake occurred, I was in India, and as soon as it occurred, all our professors, they went to Indonesia to survey the damage, to see what happened. And when they come back, they explain it's catastrophic. Some islands actually disappeared. They went under the water. Some unknown islands, they came up. So you have a tsunami force which can cause all that kind of phenomena. Japan Fukushima Daiichi nuclear disaster was caused by tsunami generated flooding. Permanent damage to the area within 20-kilometer radius inhabitable area resulted in more than 150,000 to be relocated. So what happened in the nuclear accident? The way nuclear power plant works, it needs a constant cooling. The power plant is designed to shut down immediately. Once an earthquake occurs, depending on the magnitude, all nuclear power plants in the world, they are designed to automatically shut down. But you shut down doesn't mean that the nuclear will stop. Reaction doesn't stop. So you need a constant cooling of those nuclear bundles. Once you initiate a nuclear reaction, it takes years. So you have to cool it down. But what happened in Japan is the tsunami came. The vibration is fine. It did nothing to the nuclear power plant. But the tsunami came and flooded the entire nuclear site. So those cooling systems, the pipes, everything, they get flooded. They stop working. So what happened when the water receded? There is no water cooling the nuclear bundles. So the nuclear meltdown occurred, pressure increased, and then explosion. So you need to, it's not, nuclear power plant is very unique. You need to cool it down. That's why they usually build it very close to oceans, lakes, or water, because you need to constantly cool down those reactors, the nuclear rods, they call it. So if you don't cool it, then it melts everything. Even the metal reactor pressure vessel, where it's included, it will be melting. It melts everything. They call it partial meltdown or complete meltdown, depending on how bad it is. And pressure increases, and finally it exploded. And because of that, now that area, because there is a radiation going on, within 20-kilometer radius, it's inhabitable right now. And for the coming several decades, cleaning is not an easy job for a nuclear radiation. And 150,000 people that are relocated, they cannot come back to their home anymore. Maybe hundreds of years after cleaning is done. So some more picture from the 2011 Japan earthquake damage. You see how buildings thrown apart. Another example. So we saw tsunami examples. Let's see another damages, or like the 1964 Niigata Japan earthquake, which is a magnitude of 7.6. There were 3,534 houses destroyed and a further 11,000 were damaged. This level of damage is explained by the influence of poor subsoil condition. Most of the lower part of the city of Niigata is built on mainly consisting of loose sand. So this is another phenomena called liquefaction. When the entire city is constructed on loose sand, and during the shaking, what happens is that loose sand tries to densify. But at the same time, when it tries to densify, there is water in it. So it's creating pressure. At some point, the pressure exceeds and tries to escape and liquefies everything. So what you think of like a loose sand, a solid deposit, actually it turns into liquid. The whole area turns, or partial areas turn into liquid. That's what the term liquefaction refers to. Shaking during the earthquake created liquefaction, a state where soil becomes semi-liquid and loses strength due to the earthquake shaking. So that's where the Japanese and where the earthquake occurred. Oh, this is the phenomena of the liquefaction. You can go through it, you can read it. But in a model, if you have a loose sand, let's say a building site, you have a water table at some depths below the ground. But if you have a loose sand, when the seismic motion comes and shakes this loose sand, the sand tries to densify. But when it densifies, it's actually also pressurizing the pore water, the water inside the pores. And at some point, depending on the shaking, what happens is the pore water underneath exceeds the pressure from the top, the surcharge pressure. And the pressure tries to exceed. You see this water coming out. It's called the sand blast, the water coming out and with the sand. So in that case, what happens is this entire area turns into a semi-liquid. And you may have differential settlements or even a water coming out to the surface, creating some ponds. And what happens is, because water is coming out, you see this settlement. Before the liquefaction, the ground surface used to be here. After, because the water is coming out, entire thing is settling down. You see, you have some part of settlement, entirety. And it may be more sand blast in some areas than the other. The whole building can collapse, can be swallowed, or partially like a differential settlement. So this is what pictures afterwards. You don't see the water in this case. but the sand blast, you see some holes created. This has also these holes are because of this sand boils, because the pressure of the water is taking some sand and going to the surface. That's what liquefaction does. So you have, like, these are reported damages from the 1964 Niigata, Japan earthquake. Some buildings, collapsing, the entire building falling sideways. It tells you that this area is liquefying. Or some spots you see turning into liquid, cars being swallowed. Or a partial settlement, you see this pile foundation. So the entire thing is unstable underneath. Let's see another example with another phenomena, the 1985 Mexico City earthquake. It occurred in 1985 with a magnitude of 8.0, 320 kilometers away from the city. So this is Mexico City, and it occurred right here on the shore. It's about 320 kilometers away on the west-south area. Quick occur a tectonic tension between the subducting Cocos plate and the North American plate. So this is oceanic plate. The Cocos plate is going underneath the North American plate on the picture on the right side. So there is tension going on there. So that's just more example how that plate movement is the Coco plate going under the North American plate. You can see this is like a convective current as we talked earlier. The Coco plate underneath going, and there are mountains actually over there. If you see mountain on the ground surface, especially near to a shore, it's a clear sign that there is a converging plate going on. You see these mountains in the west part of US, like California, it's a range of mountain, it's clear. In Asia regions or the west part of South America. So now, give me 1 second. I'm having a call in the middle of this class. Okay, I'll call back later. Oh, give me a second. Let me respond quickly. Okay. So in Mexico, what happened is the earthquake happened on the land, but so there is no, we're not expecting tsunami. But what happened is there is a phenomena called resonance. Depending on the soil deposit you have, when the earthquake comes, it vibrates, the entire interior of Earth, especially around the earthquake. So in Mexico, the entire city is built on this clay deposit, a loose lake clay sediment. This is Mexico City. The earthquake comes, you see this on the bedrock, there is some vibration. And when it vibrates the soil has its own mode of vibration. We'll talk more detail later, but for now, just take away, there is something called shear wave velocity of the soil. This is a property of the soil. Chapter 5, a dynamic property of soil. We'll talk more about it. Different soil have different shear wave velocities. This soil underneath of the Mexico City, it has 80 meter per second shear wave velocity. And it has a height of from bedrock about 40 meters. So there is something called the fundamental frequency of a soil. You can determine by shear wave velocity by 4H, 0.5 hertz, or the period is around 2 seconds. Then, so what happens is, if when it comes here, there is a phenomena called resonance. It's a situation where extra large vibration amplitude occur when the natural period or frequency of the building closely matches with natural frequency of underlying soil. So this 2-second period, it's the fundamental vibration of the soil. So what happens is, because of this motion, if there be for buildings whose fundamental frequency is close to 2 seconds, if it matches, that's where you have a resonance. You will have a more amplified motion. So the most damages was in Mexico City because of its subsoil condition. The city is built on what is used to be lake, loose lake clay sediment. It used to be lake in the past, maybe thousands, millions of years ago. So it's a soft deposit. The loose soft clay amplified the earthquake about 5 to 10 times compared to the outside city with better subsoil condition. So what happens when it comes from the rock and goes to the soil, so soft deposit, there is more amplification happening within the soil. We'll talk later why it amplified more. Certainly, depending on the soil type, you have amplified motion, or you can have even de-amplified motion. But this amplified motion with a fundamental period of the soil, which is 2 seconds, when it matches closely with the frequency of buildings, fundamental period of buildings, that's what is caused the most damage. We will see what you don't understand this concept right now, but we have a chapter later where we talk more on theory of vibration and how fundamental frequencies are determined for any object, any vibrating material, buildings, soil, even a beam. And we'll talk about what resonance exactly is. But resonance for now, just take it when the periods of two things closely match, you have amplified motion. So buildings from 5 to 12 in this range, 8, 10, 12-story buildings, depending on their framing, there is a way to calculate the period of a building depending on the framing, beams, columns, shear walls, everything. So those which are close to 2 seconds, they match with the vibration of the soil. So that's where we observed the most damages. So this is another response spectrum plot. We'll see it more detail in chapter 4, but you can have a time history record for earthquake, or you can convert it into response spectrum. So when you convert the response spectrum, you can clearly see the periods and the dominant frequencies. For example, in this case, this peak acceleration occurred around 2-second period. This period is not the time duration. Even if they have the same unit, when we talk about period, it's the property of the structure or the soil. So don't get confused with time, which is measured in second also. So the spectral acceleration, so there are these two earthquakes. Now, if you see it, this is the bedrock motions at the bottom area. The bedrock motion, they are very low accelerations. For example, the spectral acceleration, the blue one, which is the 2017 or earthquake, there are two earthquakes right here. The 1985 is the pink one. So if you see the 1985, this one, the maximum at bedrock, which is a rock, Tsunami is the site where they recorded it in Mexico. So the blue one, we have, let's say, this one, which is around, this is pointed to 0.1, around 0.09, 0.08 G acceleration at the peak, around maybe 1.8 second. This is at the bedrock. But when it moves through the soil, this is how much it's amplified. It gets 0.6 G. So it's like a 9 or 12 times. One of them is 9 times amplification, 1985. So this one is 9 times, and you have this lower here. So this one is amplified 12 times. So whatever seismic comes to the bedrock here in the previous slide, it was actually amplified 12 times on the ground surface. You see this red time history. So that's how much it is amplified. The soil amplified it. Most soils amplify the earthquake. When you go from rigid object to a softer material, it amplifies the motion. So that was the cause. So the motion was amplified, and it matches the resonance frequency of the soil on some of the structures, then damage occurred. So you may not understand the whole concept in this response spectrum plot, but it will be clear as we go further into the course. So this is just showing you another model where it selectively attacks some structures only. Some short structures, very rigid structures, they were not affected. They didn't collapse at least. Some structures where fundamental period is around 2 seconds, that's where the more damage is. It's not height only. It depends on the framing and the shear wall, beams, and columns inside the buildings. But in general, buildings with a story of 5 to 15, those are where they observe the most damage. Tall buildings, they didn't get damage because the period is far away from 2 seconds. So these are pictures from the 1985 Mexico City earthquake. More damages, buildings collapsing, mid-range building collapsing. You see tall buildings, very little damage, standing intact. Maybe some window cracks, some concrete, floors and wall cracks, beam cracks, but no collapsing. So that's a phenomena called resonance. So even without tsunami, without water, depending on the soil type, you can have this resonance damage, even without liquefaction. So one example we saw was flooding, tsunami. The other was liquefaction. This is totally different phenomena. It's called resonance. But it will be more clear if we go into, theory of vibrations and property of, the soil and the structure. So this is another contour map where it shows you the 1985 damages in those buildings and the 2007. They have a code revisions because every time they observe something, bad damages, they revise the code. So you see it in 2017, more requirement enforced on designers. Could building codes updated? So you see less damage in 2017. But in 1985, see how many buildings are damaged. Other earthquake damages on civil structures, you can have landslides. Landslide can occur by, seeping water through the ground. But if there is an earthquake also, it can accelerate that phenomena. So major damages, landslide in Peru, you can have the whole portion of the mountain sliding on buildings or roads. These are Google images just to show you to help us understand, but you can look more in Google to see, what other damages can be. Or structural foundation or bearing capacity failures. Buildings, collapse of Showa Bridge after 1964 Niigata earthquake. Or a Taiwan earthquake, several buildings leaning near collapse. Alex, you're around there, I don't think this building is right there right now. But, where you are in Taiwan, that's very high seismic area.
Yeah, I think it's 1997, right? 1997, a high magnitude earthquake has been happened.
Yeah.
Around 7.5. That was a catastrophic failure. Around 3,000 people have been died that time. And a month ago, I think, in central part of Taiwan, 7.2 around has been recorded.
Yeah.
And one bridge is totally damaged. This is the record as far as I know in Taiwan.
Exactly. Recently, what the world, the design community is learning is based on the data from previous earthquakes, we are revising our design codes. It's becoming very stringent. So we know what phenomena are causing it. Something like tsunami, or we are building walls. Something like liquefaction, we are mitigating liquefaction by adding something to the soil or reinforcing it. Or buildings, we change, the foundation type. We'll see it later in other chapters. But right now, buildings in Taiwan, In Japan area, they are using base isolation. So they dampen the earthquake before it gets into the building. So there are many techniques nowadays being applied, which is reducing the impact. Thanks, Alex. So let's see seismic waves, trying to understand, okay, if this is a damage we can have from earthquakes, and then how earthquake is traveling from one place to the other. It's in the form of waves, a water wave. If you drop some stone on water, then you see waves on the surface traveling. It's a similar phenomenon happening for earthquake. We call them wave. It's the energy propagation. So earthquake vibration originate from the point of initiation of rupture and propagate in all directions. This vibration travels through the rock in the form of elastic waves. So you can have an earthquake occurring, at some point you can see the picture on the right side. And the waves can go to deep inside to the earth. We call them body waves. Those body waves can come also on the surface, and they can move like a water waves. We call them surface waves. So we can have two kinds of waves, surface waves and body waves. Body waves, if it's a major earthquake, if it happened, let's say in Asia, it can be recorded in Europe or in North America because we have the body waves traveling. So seismic waves in general, we can have body waves and surface waves. Body waves, we have primary wave and secondary wave. Primary wave is the wave which arrives first. We call it primary. And secondary wave is the wave which arrives after the primary wave. In secondary wave, we can have horizontally propagating or vertically propagating shear waves. Secondary waves are also called shear waves, depending on the particle propagation. If you come to surface waves, you can have lava waves and Rayleigh waves. We'll go a little deeper into it. This is how the waves look like. In a P wave is primary wave. It travels by compression and relaxation. You can have an expansion and compression. So if you hit it like axially, that's what the propagation looks like. S wave, give me 1 second. I have a disturbance from my daughter. Okay, I'm back. So the primary wave, they have a compression like axial traveling. You have a compression phase and expansion phase. In terms of shear waves, the particle propagation, particle motion is perpendicular. You see it up and down. But the main wave propagation is like you see it in the red arrow. And lava waves, lava waves and Rayleigh waves, they are surface waves. So we see them on the surface. In case of Rayleigh wave, you see it like a water wave, up and down. But the particle motion, it looks like circular if you take a section on the Earth. In the case of lava wave, it's sideways. Particle motion is sideways, and which is also perpendicular to the main wave propagation. like I said, P wave. You can see an example of like.
ዶክተር ይሰማል?
ይሰማል. Go ahead.
ምናልባት ሰዓት በእኛ 5 ተኩል ሆኗል 11 ሰዓት ተኩል ማለት ነው።
Okay. Let's just, we can stop it right here and we can continue next time. Let me see. We have about 20 slides, I believe. 25. I think this is a good point. We can stop here and we can continue next Monday.
Okay.
Okay.